All right, let's go ahead and start back up. So let's look over the amino acids I'm sure we all have memorized. Okay, glycine. Remember the R group is hydrogen. Alanine, CH3, it's methyl. Proline is the ring, so it's CH2, 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 back to nitrogen. Valine, this is your isopropyl group, so it's like a V. Leucine is isobutyl, so you still have your V, but one extra carbon in the chain. Isoleucine, it's a sec-butyl, meaning it's connected at the second carbon of the butyl chain. Methionine, what in this name do you remember I said that tells you there's a sulfur in there? Thio. So this has your sulfur, so you have CH2, CH2, sulfur, CH3. Then we learned a couple of aromatic. We have phenylalanine. What does phenyl mean? Or what benzene? That means there's a benzene. So phenylalanine, so there's a phenyl group of benzene with alanine, which is CH2. And then tyrosine is similar to phenylalanine, except it has this alcohol group, which now gives it hydrogen bonding. So to make sure we get all of them in, we had to learn 4 today. I know. I know. We can survive 4. Tryptophan. How do you know tryptophan? Turkey. Exactly. This ring right here, do you see there's a benzene ring? When you join these 2 rings together, this is called an indole ring. I-N-D-O-L-E. Indole. In the R group down here, is there any hydrogen bonding? Down here? No. Can anything accept a hydrogen bond? Yes, the nitrogen. So it cannot donate a hydrogen bond, but it can accept one because of this hydrogen here. This one is essential. Tryptophan in your body is converted into melatonin. What does melatonin do? As you sleep, and that's the reason it has that sedative effect. Or it does take a lot to actually have that effect. And then it's eventually turned into serotonin, which kind of gives you that happy feeling. So that's tryptophan. Oh. Okay, and that's all of your aromatic. So we have tryptophan, tyrosine, and phenylalanine are in your aromatic group. So today we're going to learn 3 of the polar uncharged groups. Polar, what does that mean? Not dipolar. It just means it has an electronegative atom in the R group. Uncharged meaning it's not charged. So the first one is serine. What's my electronegative atom in this R group? The oxygen there. Can this one hydrogen bond? Yes. Any of yours with alcohol, they can hydrogen bond, and they can also further react. Phosphonates are very similar to carbonyls, except instead of a carbon there, it has a phosphorus group. So alcohol is a decent nucleophile, so it'll, like it, we've seen in class, where it'll attack the carbonyl. So basically, this is a really good nucleophile. Serine is used in your body as a neurotransmitter. It's used in enzyme production. And a lot of nerve gases inhibit serine. So you can't neurotransmit, if you want, and produce enzymes and stuff. Threonine. What is the electronegative atom here? Oxygen. Can this one hydrogen bond? Yes, and this one is essential, meaning we need it in our diet. And so you see here, the R group, it's kind of like an isopropyl, but with an alcohol coming off instead. So it's OH, CH, CH3. Okay, then the last one for today is cysteine. Our polar group here is S, sulfur, which is a thio group. This is one of the main amino acids found in your hair, forming disulfide bonds. The curly, in some people's hair. The curlier your hair, the more disulfide and more cysteine you have in your hair. So when you use like a straightener, and I'm not talking about one you plug in the wall, I'm talking about a chemical straightener, it breaks those disulfide bonds to straighten your hair. This is also a really good antioxidant. So those are all of the ones for today. So you have tryptophan, which has that end-bell ring, serine, which is a CH2OH, threonine, which is sort of the isopropyl with the alcohol, and cysteine, which is the CH2SH. There are more. Yeah, there's, I think, 2 more. Yeah, 2 more. Okay. So the new reactions we learned yesterday, the first one hold on. What will the first one do? Reduce it to what? OH. Will it do anything to the double bond? No. So your double bond will remain there, and your carbonyl will turn into the alcohol. What about the one below it? Yeah, so the carbonyl will turn into an OH, and then will anything happen to the double bond? Yeah, it will turn into a single bond, so it'll be gone. So what does the first one do? It's a reduction. What does it reduce it to? Not an OH? Just the hydrogen, yeah. So it completely gets rid of the carbonyl. So I have 1, 2, 3, 4, 5 carbons. So 1, 2, 3, 4, 5. It completely reduces the oxygen off. What about the one below it? It eats it, so it's the same thing. The only difference between these, this is in acidic conditions, this is in basic conditions. But it gives you the same product. What does this one do? Not a green yarn? Sort of, yeah. It adds what? Carbon group where? It replaces what? Sort of. But what part of it? Just the O, yeah. It's just going to replace oxygen, so that double bond is still there. So you draw this, just as you see it, like that, minus the oxygen. Now how many carbons in this group here? 4. So that top carbon is considered one of the 4. So 1, 2, 3, 4. Any questions with any of those? Okay. Then we learned a little bit about chapter 19. If you're naming an amine, what does it end in? Amine, right? How do we know the difference between a primary, secondary, tertiary? Yes, the carbon's coming off of that nitrogen. In naming, how do we, quote-unquote, number carbons coming off that nitrogen? N. We put an N there. What is benzene with an amine coming off of it? Do you remember what that's called? Like, that. No, phenol would be the alcohol. Has nothing to do with pH. It starts with an A.
Yeah, I'm just shooting in the dark here.
Aniline. You're just slightly off. Do amines smell very good? No. Can amines have hydrogen bonding? Yes. Do all amines have hydrogen bonding? No. Can an amine be chiral? Yes. So it could be the carbon coming off the amine is chiral, or the nitrogen itself is chiral. And are amines typically acidic or basic? Basic. They can also act as a nucleophile. So it's about where we stopped at. Okay, and we looked at a little bit at this at chapter 16. So remember when we were just deciding if something was aromatic or not? And then you need to decide, are you going to count those electrons, that lone pair? And in this one, in this structure here, would you count that lone pair? Yes, to be aromatic you do. So are those available to bond? No, not really, because you have to use them to be aromatic. So do you see here the pKb is 13.6. Now if I come back here, these typical pKbs were, between 4 and 3. Okay, so this is a lot higher. So the reason is because these lone pairs here aren't as available to bond to hydrogen, because what does a base do? What does it want? A hydrogen. So if these aren't available to bond to hydrogen, that means there's nothing there to take the hydrogen off. So this is considered, we'll just say a really weak base. And then we looked at this one here, for example. Now, do we need these lone pairs? Do we need to count them? No. So is this going to be more or less basic? More basic, because now you don't need those electrons to be aromatic, so they're available to bond. So look at the pKb, it's 8.75. And if I look over here, this one was 13.6. So you see it's getting lower, meaning it's more basic. And then if we look at this one, this is the one we haven't really looked at. Can this structure right here be aromatic at all? No, it's non-aromatic if you want. There's no double bonds in here, nothing to resonate. Okay? So are these available to bond? Yes, because it's not stabilized at all. And look at this, the pKb is 2.88. Anytime you have resonance here, do you see these double bonds? Will stabilize something, or anytime resonance stabilizes. So this one, does it have any double bonds to stabilize it? No, so it's more reactive, so more basic. Okay? So the most basic you can get is if a structure is not aromatic at all. Okay, there's nothing there to stabilize it. So there are three choices basically. We'll say this is the most basic with no double bonds. This is sort of, we'll call it mid-basic, where it has the double bond stability, but you don't need those electrons necessarily to have that. And then the least basic will be when you actually need those lone pairs to resonate to be aromatic. Most amines do not have double bonds. Okay, so most of them are pretty basic. Okay, and just a review over IR. Remember that an amine will come in around the same area as an alcohol, but it's a lot narrower. Remember, the alcohol was the really broad peak. It would take up like this whole area here. But if you had a peak, you see these are pretty significant, okay, but they're a little narrow. So this would be your amine. And how many peaks do we have here? 2. So how many hydrogens coming out that amine? 2, the same answer. Yeah. So if I just had one narrow peak, then how many nitrogens? 1. And NMR, don't worry so much about that because it'll come in different areas. Okay, so here's our first reaction for this. And let's just look at overall what's going on. Okay, we'll do the mechanism. What is this? What am I starting out with? In this case, they kind of show it as a ketone. Okay, and they're saying you could also use an aldehyde. But so we have a ketone. And then, do you see that this is an amine right here? This blue. So when I have a ketone with an amine, and you see it has this Y group means it can be anything coming off. Okay? It could be another hydrogen. It could be a carbon group. It could be an alcohol. It could be another amine. Okay? So just think an amine with something else. Okay, just attached to something else. So that's why they put Y there. Now let's look at overall. Look at my final product. Okay, is that oxygen in the carbonyl there anymore? No. What did it leave as? Water. You can see right here. Here's my nitrogen. Now here's the original. Does it have those 2 hydrogens there? No. How many hydrogens does this oxygen need to leave as water? 2. So does it make sense that it's probably getting it from those 2 right there? And then the Y group. Is the Y group still attached? Yes. So now let's try to figure out what happens in the mechanism here. So when you have a double bond oxygen, that's called a carbonyl. When you have a double bond nitrogen, that's called an imine. I-M-I-N-E. All right, now based on what we just saw, let's predict the product. We'll look at the mechanism. Is oxygen on there? No. What's attached there? Not an issue. So we have is the double bond still there? Yeah, the double bond is still there. We have a nitrogen. Does it have any hydrogens on it? No. But what will be attached? CH3. That's my Y group. So basically this part right there will replace the oxygen. Okay, so we have, over the arrow, we have a nitrogen and a carbon. Which one's more electronegative? Nitrogen. So that's the one that's going to attack. Remember, it can act as a base or a nucleophile. In this case, a nucleophile. Where do you think it wants to make a bond? The carbonyl. And what do you think happens to those electrons? They're going to go up there. Okay, now things like to neutralize if they can. That oxygen, what does it want? Probably a hydrogen, and then where can it get a hydrogen? The nitrogen. So it's just going to pull off that hydrogen so it'll neutralize the nitrogen at the same time. All right, now in the final product, how is the nitrogen bonded? A double bond, and the OH is gone, right? So I can push these electrons down, and what will leave? OH, and what will it grab at the same time? A hydrogen. All right, so on this part right here, did we do anything with these methyl groups? No, so I can make these into, 5 carbons long each, right? Or I could put a hydrogen there. Would it matter? No, so this can change. The carbons coming off of there can change because where's the reaction taking place? Right there at the carbonyl. Nothing else really matters. And then if I look at this methyl group here, did I do anything with that methyl group? No, it just kind of sat there the whole time. And that's why they call, like shorthand, they'll just put NH2Y. I mean, nothing's going to happen to that Y. That Y will be there, okay? So this can be whatever I want, and these carbon groups can be whatever I want. So if we have, just predicting this product here, write down what you think will happen there. Okay, what changes? The carbonyl, how does that change? Yeah, there's a double bond to nitrogen now. And what's coming off? Just the OH. Any questions on that one? Okay. Okay, so this one's just interesting. I just want to show you so you can see some practical use of these. So this is an amine right here. Okay, now this is a sulfonyl. Do you see that's kind of similar to a carbonyl? Okay, so like with the carbonyl, this nitrogen can come in, attack the sulfur, and you can have your leaving group leave. Okay, so now I have this sulfonamide, sulfur now attached to the amine. Chlorine's your leaving group, now your amine's attached. Okay, now the purpose of these, this is actually sulfonamides is a class of antibiotics. Okay, so let me show you how they work. Okay, so this is folic acid. Okay, and bacteria use this basically to grow and reproduce and everything. Now, do you see this green box right there? That's the part that's important. So normally folic acid looks like this. Okay, but when your sulfonamide inserts itself in, if I come back here, I was just calling it R group. Okay. The big part right here, see this sulfur kind of carbonyl group? You see it's 2 oxygens? What happens here is this sulfur kind of carbonyl will insert itself into here. Okay? So you'll have your S, double bond O, double bond O. And that's your antibiotic that you're inserting into there. When that occurs, this basically inhibits the growth. It no longer recognizes this as folic acid because it's not folic acid anymore. And it kills the bacteria. Anyway, so that's how that works. So the sulfonamide inserts itself into the production of folic acid so that it's no longer produced. Anyway, so then you can see a practical application of these amines. Okay, Hoffman. Do you remember, at least, does the name sound familiar? Okay. This has to do with double bonds, elimination reactions. Okay, so there's Hoffman and there's Zaitsev. Do you remember between the two, which one went to the more substituted side? Zaitsev. So Hoffman would go to the least substituted side. Okay, so like the least stable. So in this reaction here, let's see what's going on. So here, this is just an amine. It doesn't have to be cyclic, okay, it's just an amine. All right, and then I have this methyl iodide right here in the first step. Now, amines are highly reactive towards alkyl halides, like this. Meaning they can't stop reacting. So what you do, you'll put an excess of like methyl iodide, and basically all of your, it's going to take up all of your lone pairs in the nitrogen and all of the hydrogens, okay? So a nitrogen, the highest you can have for a nitrogen is quaternary, meaning 4 bonds. And so this carbon group that you're trying to add will basically take up all of that it can. So it'll replace lone pairs and hydrogens. So how many hydrogens do I have? 2. And then lone pairs? 1, so a total of 3. So do you see I have 3 carbon groups that add there? Okay? So basically it's going to add enough carbon groups so you have 4 total. And this carbon group was already on there, so that counts as one of your 4. So I can't stop. It makes this group right here. Now the point of this is this. You see now I have a positive on my nitrogen. Okay? Now this is a really good leaving group. So is alcohol a good leaving group? No. What does it leave as? Water. And when water is on there, it's always a positive charge if you actually show the water molecule on there. And this is how you make basically nitrogen into a good leaving group. So you don't add hydrogen to it, you can add carbon to it very easily. So now I have this really good leaving group. But how many carbon groups are coming off of here? 3. Does that seem pretty bulky? Yeah, it is very bulky. So basically what happens, now this right here is your base, and it's going to do an elimination, which means form a double bond, and it's going to take off a hydrogen at the least substituted side, because it's already bulky. There's already not a lot of room. It's really crowded. So it's going to go to the least crowded side. So if I have something like this, let's draw it. This would be better. And then let's use the base hydroxide. Okay, what will the first step do? Yeah, it's going to add 3 CH3s onto the nitrogen. Oops, 3. Think of it. This is bulky. Okay, now to decide all the places you could take a hydrogen off, do you see that the nitrogen is connected right here? So that's where it's connected. That's a carbon. That's one of the carbons for the double bond. Now, to make a double bond, I need 2 carbons, right? So look to every carbon attached to it. How many carbons are attached there? 2. So I'll put X and X. Now, between the 2, we'll say the left and the right, which one's the least crowded? The one on the left. It has the least amount of branches. So my base, so I'm going to take a hydrogen off there. My base, which is hydroxide, comes in, grabs that hydrogen, and where does hydrogen leave its electrons? But right here to make a double bond. And then this whole nitrogen group right here is now my leaving group. So my final product, put my double bond right there. And that was my leaving group. So what's the point of step 1? Yeah, to make nitrogen into a good leaving group. And in this case, a bulky leaving group. And then what's the point of step 2? make the double bond. So you need a good leaving group first, so that's the point of step 1. And then step 2, now that we have a good leaving group, now you can do your elimination, make your double bond. So these sometimes can be kind of tricky to determine where to put the double bond. Let me show you one, and I'll tell you right now this is tricky. So I'll write this one down and see if you can figure out where it goes. You can work in a group or whatever. Okay, and see if you, and I'll tell you, I'm warning you, it's not as easy as it looks. Okay, so see if you can figure out where to put that double bond. Okay, so let's look at this one. Okay, what will the methyl iodide do? And how many CH3s? Not 3, but 2 in this case, because I already have 2 carbon groups on there. So I'll add 2 more. So I'm just going to cheat and put them on there. Okay, so I did step 1. Okay, now step 2. Now this is the harder part here. Now you have to put all the possible places that you can have a double bond. So the first place I always check here, nitrogen's connected to this chain. Now how many positions do I need to look at? 2. So you can either go to the right or to the left. Now is there any other carbon group that you can put a double bond on? Where? Right here. Here and here. Why didn't I choose methyl? How many carbons do you need for a double bond? 2. Does a methyl have 2 carbons? No. So you don't even have to look at methyls. So let's look here. Between these 2 right here, we'll say the right and the left, which one is the least crowded? The one on the right. Now look over here. Now this whole thing is connected to a chain. Okay? Now basically look at which one has the shorter chain. We'll say the top or the bottom. The bottom. So this is where your double bond is formed. So then your double bond ends up becoming CH2, CH2, because you're going to take a hydrogen from here. And then what does my leaving group look like then? So I have nitrogen with how many methyls? 2 methyls. And then it's also connected to that chain, right? So this whole thing is my leaving group, if you want, and then this is my double bond. So I try to warn you that this one's a little more difficult, right? It's that ethyl group there that you forget to look at. So look at any carbon chains coming off nitrogen that have 2 or more carbons. Okay? Methyls, they don't matter because you can't have a double bond there. But anything greater than methyl, check to see if you can put a double bond there. Yeah, what happened, well, what it does, let me put a 2 right here. 2 and hydrogen. It comes off, it takes that hydrogen. Hydrogen will leave its electrons right in between the 2, which causes that to leave. So it does an elimination right here, as that is my leaving group. If you want, I'm just going to call it X as my leaving group because it's giant, so it can be distracting sometimes. Your base comes in, grabs hydrogen, leaves its electrons, which makes the leaving group leave. Okay? And X in this case just happens to be this giant thing right here. Before we take a break, we did have a request to do a few of the sapling. I won't do all of them right now. We'll do one and then we'll take a break. We're going to do 13, 14, 15. All right, let's look at this first one. I'll warn you too, in your sapling for chapter 19, it has a Hoffman, and in the next reaction we'll do is called a Cope. They're almost identical. You know, it has some fun ones in there. Okay, let's look at this one. What is this? A ketone. What is this? Alcohol. How many do we have? 2, so how many do you think we'll add? 2. Do you remember when we had our protecting group, our little hat? How many alcohols on there? 2. So this is almost the same exact reaction, except they're not connected together. Okay? So in the end, do you remember, was that carbonyl oxygen on there anymore? No, it was those 2 oxygens off the side, right? And they're just where were they bonded? Yes, that carbonyl carbon. So how this one will look, just draw it really quick. So this is that base right there. Now, and we said those alcohols are connected at the carbonyl carbon, right? So we have, I'll put the oxygen there in a second. Oxygen, carbon, carbon, oxygen, carbon, carbon. Hold on. Oxygen. There it goes. So do you see, again, how many alcohol groups do we have? 2. And how many did I add onto there? 2. So it's knowing that these 2 alcohol groups basically will replace that carbonyl. It's, again, same reaction. Do you see that if I had the protecting group on there, it kind of looked like this, right? Those 2 oxygens coming off, except they were connected on top here. Okay? These just aren't connected across. They're just 2 different groups. But do you see that it's the same reaction, just not a ring? So that's that one. So let's take a break and then we'll look at the other 2. All right, let's go ahead and start back up. All right, the easiest thing to do for this one is to go backwards. Let me see if the hint is good to you. No, it doesn't. Okay. Did any of you look up what acetaldehyde was? Which was, well, an aldehyde is what? Carbonyl with a hydrogen. And then what's the carbon group coming off of there? CH3, just a methyl. So it's a aldehyde with a methyl. Okay? So do you see right here, so of all of this area right here, so acetaldehyde is part of this. Okay? Do you see that the carbonyl would have to be right here? Why did I know it had to be right there? What gave it away? The alcohol, the oxygen there, right? To have a carbonyl, you need the oxygen. Now, was the acetaldehyde from the left side or from the right side? The acetaldehyde, so there's, the acetaldehyde is methyl with an aldehyde, okay? So looking over here, so this is where the carbonyl is. We're trying to figure out what part of this was the acetaldehyde. So could it have been the carbon group to the left? No, could it be the carbon group to the right? Yes, because that's the methyl. Do you see coming off of there is a methyl? Okay, now do you see when we have magnesium on there, what is that? Grignard. And what does Grignard do? It adds what type of group? An R group. So if this was acetaldehyde, what R group did I add onto here? This 1, 2, 3 carbon group there. So it would have been 1, 2. This is my R group. That's acetaldehyde. Okay, and then how it's drawn on there is like this. So if you want to put that as CH3. So do you see that this side here is similar to this here, just with carbonyl? And so what did I add? There's not a hydrogen. Well, there is a hydrogen. It's hidden. But what did I add in addition to all this? The carbon group. Oh, I added too many carbons. Okay, I added this carbon group there. Now with the Grignard, how does that look? What's connected there? To make this carbon group want to attack there, what's coming off here as a Grignard? Magnesium with a halogen, right? I don't know if this one specifies. No, it doesn't, so you can use any halogen. Okay, so let's say magnesium bromide. Okay, so if I reacted these two together, what will the carbonyl turn into? An alcohol, right? And then what carbon group am I adding? This one, right? The purple group. 1, 2, 3. And that was your final product there. So the first part, or if you want going backwards, is figuring out what R group did you add to acetaldehyde to make that product. And in this case, it was this. Okay, now let's go one step further, because there's two things it wants you to draw. Magnesium. So what do you think, if I had just magnesium there, what do you think I'm adding to here? Just magnesium, okay? So take the magnesium out. So my R group I added 1, 2, then here would be, there you are, magnesium, nope, Okay, magnesium bromide. That's my Grignard I'm adding onto here to make that. Now, we said the difference between this one and this one, do you see what I'm adding magnesium on the arrow? So basically take your magnesium out. So draw this same thing, 1, 2, and then 3. Now instead of magnesium there, what will I have? Just bromine. There. Does that make sense? So this is a Grignard, you're going backwards. You're trying to figure out what R group you have. Then they added this step here to see if you can figure out, the difference between. So this is an alkyl halide. This is the Grignard. And to go between those two, so to make an alkyl halide into a Grignard, you just need to add magnesium. Ether is your solvent. Solvent. This is what it's all dissolved in. Ethers are almost always solvents. So here, an alkyl halide is a electrophile. Okay? We will have like nucleophiles attack it, bromine leave, right? So this is a really good electrophile. I add magnesium to this, and now what's the charge of that carbon right there? Negative, right? So now it's a nucleophile. So that's why this step is important. It's changing your electrophile into a nucleophile. Okay? And the only thing you have to do is add magnesium to it. So that's that one. And then the final one here. Okay, so let's look at the difference here. What type of carbonyl is this? A ketone. What's this one? Ester. So it's carbonyl O carbon. It's an ester. It's an ether with a carbonyl. And then let's look over here. Did the ketone react? No. Did the ester react? Yes. So I want to react the ketone, but not the ester. React the ester, but not the ketone. Okay? So what do I need to do to the ketone so it doesn't react? Protect it. Which one looks like my protecting group? The first one on the left. Okay. Now, what reaction did I do here? I turned a carbonyl into an alcohol. What is that? A reduction. Now, do I need a strong reducing agent or a weak one? The lithium, the stronger one. Sodium borohydrate will only reduce ketones and aldehydes. So since this is an ester, I have to use the lithium. Now, how do I take a protecting group off? H, yeah, so it's going to be this one here, H3 plus and water. And then that'll do it. This one here, let's see, this one here is, they're both electron donating groups coming off of here. So this is, they both have this part coming out. So it's really just the end parts. Methyls is an electron donating group, but it's the sigma donator. It's a weaker donating group. Oxygens have lone pairs, and so it can actually donate the lone pairs to it. Carbon doesn't have lone pairs, so it's just sort of pretending to donate, if you want. Oxygen will actually donate lone pairs, so it's a stronger donator. Donating groups always stabilize. So it makes this one more reactive. So it's the same way. So aldehydes are more reactive than ketones because it only has one donating group. This one is less reactive because it has a stronger donating group. Okay, so that's your sapling hope for the day. Mm-hmm. Try. Yeah. Okay. We did that. Okay, oxidation of amines. So let's learn 2 more reactions today, and then I'll let you go a little early, okay? But you have to be paying attention, right? Okay. Really? I'd rather stay here longer. Oxidation. What do we do with oxidation? What do we add? Oxygen. Good. Now, what we're going to be doing to the oxygen, we're going to look at just tertiary amines. Tertiary amines have how many carbon groups? 3. Okay? So what it does, if you oxidize a tertiary amine, it just adds a single oxygen on there. Okay? So I think the next slide has the, yes. So here's my tertiary amine. Now usually we use peroxide to oxidize that. Don't think of that as an anti-Makarnikov, because it's also an oxidizing agent. Plus there's no anti-Makarnikov on here. So do you see that all it did, it added a single oxygen. Okay? Now when I do this, I now have 4 bonds to nitrogen, which gives it a positive charge. The reason is, how many valence electrons for nitrogen? 5. And see, there's no lone pairs, because there aren't any. And so how many is it actually using? 4. So out of the 5, it's using the 4, so it gives it this positive charge there. Oxygen, though, here is a negative because it does have 3 lone pairs on there. And it should have 6, and it's using 7. Anyway, so that's where you get your positive and your negative on there. What do we call it when we have a positive and negative? Zwitterionic. Okay, so the point of this, the purpose of doing this, is this Cope reaction. Okay? So let me draw this out so it's easier to see. And I'm going to draw it very similar to the Hoffman we did. Okay. Now, what will the peroxide do? Oxidize it. So it's just going to add that oxygen on there. How many? 1. So I'm just going to cross it out and just go ahead and draw my oxygen on there. So I have a negative charge and a positive charge on the nitrogen. Okay, does this look bulky? Yes. Now remember, anytime you have a positive charge on a nitrogen, you've made it into a good leaving group. Now when I did the Hoffman, which was the previous reaction, I actually put a base in there, right? I put like hydroxide. And let's look at where that hydroxide would take off a hydrogen. Can it take it off the methyls? No, because you need to remember 2 carbon chain. So then let's look over here. I can go to the left or the right. Which one would it take it off of? The left, because it's less bulky. So I have a hydrogen right there. But did I put hydroxide in there? No. But do you see built in here, I have an oxygen with a negative charge? So it's a base within itself. So it takes off the hydrogen. Hydrogen leaves its electrons. Yeah, do the heat. The heat will promote this. And then the whole entire leaving group leaves. So when I draw the final product, I put a double bond right here, and my leaving group was that whole entire carbon group. So you see this looks exactly like the Hoffman reaction we did. Okay? The only difference is that I put a base within the leaving group. Okay? So instead of having to add hydroxide, I oxidize my leaving group to take off the hydrogen. Okay? But do you see that this negative charge oxygen grabs a hydrogen, leaves its electrons, leaving group leaves. So this is called a co-prearrangement, but I usually just call it a fancy Hoffman. Okay, it's a built-in Hoffman reaction. So I would look at these as your final product is exactly the same. So there's one Hoffman and one co-prearrangement in your homework. But remember that final double bond product would be the same result. Okay, no matter which way you do it. So if we have, let's just predict one then. Okay, so write down what the final product would be here. Okay, where would you put the double bond? Yeah, so it would go where? To the right? Yeah. So I'll have my double bond there. And then what does my leaving group look like? And CH3 2 with OH. So this is a way, if you have this starting material and you want to basically cleave off your amine, now it could mean what you're trying to isolate is the double bond, or maybe you actually just want to isolate the amine. Either way, it's a way to cleave off an amine, to further test it if you want. Okay, then the last reaction, this is a pretty easy one. What do you think happens here? Chlorine leaves, and nitrogen attaches. How many hydrogens will be on the nitrogen? 2. Yeah, and that can leave as HCl. If I had 3, so if I have a lone pair on there, So I have how many bonds coming out of this nitrogen? 3. And then the lone pairs would be 4, 5. If you count them individually. So 5. How many valence electrons for nitrogen? 5. So it makes it neutral. So if I added, if I kept it as 3 right there, there would be no lone pair because the lone pair would take up that bond. It gives nitrogen a positive charge. So the chlorine would end up taking that hydrogen off in the end. So if we look at the mechanism, where does nitrogen attack? Carbonyl group. Electrons will go up. And in my final product, do I reform my carbonyl? Yes. And how many hydrogens on here? 2, so I need to get rid of one. What pulls it off? Chlorine. And then the question of the day, what carbonyl is that? Amide. So just so you remember, an amine, we're just going to call it NR3. R could stand for hydrogen or carbon in this case. An amide, so this is amine. And an amide, I should call that R. Is basically an amine attached to a carbonyl. So their names are similar because they are similar. So one is just an amine. One is amine attached to a carbonyl. Kind of like, so ether is ROR, which is similar to an ester, which is carbonyl OR. So those names are similar because they are similar. So an ester is an ether connected to a carbonyl, which is the same as kind of like your amide. And then that's it for the day.